All right, as you can see, this video is titled Manipulating, then L'Hopital's Rule. So basically, our goal is to have 0 over 0 or infinity over infinity. So what happens if the book gives us a problem that looks like, and they probably have something like that. Okay, if I plug in 0 right now, what you're going to end up getting is you're going to get 0 times, and then this is actually positive infinity because the cosecant graph, as I'm approaching 0 from the right, is actually going to positive infinity. So the question is, what is 0 times infinity? Now, some students will say, isn't it 0? Sometimes it is. So I want you to think about it. Technically, when I'm doing a limit, I am saying that this is going to 0. So this is like having like a super small number. Okay? And if this is going to infinity, this means it's a huge number. So if I take 1,000,000 times not quite 0, does something survive? Or is this so small that it doesn't matter how big this is, that it will still slam to 0? So that's the weird debate. So when you think about 0, it's not exactly 0. It's a very small number. So is a small number times a huge number, is there some sort of surviving value? Or will it actually go to 0 overall? That's a really weird idea. So how are we going to solve it? So how we're going to solve it is that we are going to use manipulation to get it as a fraction. So we don't see a fraction right now. However, I can easily rewrite cosecant so that it is sine. Okay. Fraction. Does it fit L'Hopital's rule? It does. So now I can go ahead and answer this question by using L'Hopital's rule. So when I do L'Hopital's rule here, the derivative of x is 1, the derivative of sine is cosine, and now I'm going to plug in 0. So what I end up getting is 1 over the cosine of 0, that's 1 over 1, 1. Why did I gasp? Because in this instance, 0 times infinity ended up equaling 1. What? Okay, again, it's that idea of this isn't really 0. It's like little fractions of a penny. And this isn't just a gigantic number. Basically, this relationship between the two is one such that we end up getting 1 when I multiply the small number times a huge number. Weird, right? At the same time, I love calculus. Calculus figured it out for me. That's amazing. Okay, so I want to show you another one that's actually a lot trickier. And this problem is the limit as x goes to infinity over 1 over x squared. And then, oh, I lied. It's x squared times the sine of 1 over 4x squared. Okay. All right, so if you've done the previous trig problem, your first instinct may be that in order to turn this into a fraction of infinity over infinity or 0 over 0 is to rewrite the sign as a cosecant. And that's a good instinct. I'm not going to be mad about that. Okay, so I do have a fraction now, so that's the good news. And this would be infinity squared, which is infinity. The cosecant of this will be 1 over infinity, which is 0. The cosecant is 0 as I approach one side is infinity. As I approach the other side, it's a negative infinity. So we'll just call it infinity. So it does check out. However, what happens if you actually use L'Hopital's rule is when I do the derivative of the bottom, it turns out that we're going to get a chain rule and we're going to get some survivors out front. We're going to actually end up in a bad situation. Here, let me just go ahead and show you what happens. All right, so if I do L'Hopital's rule on this problem, I'm going to get 2x on top. The derivative of cosecant is negative cosecant cotangent. And then I have to take the derivative of 1/4 x squared, well, 1 over 4x to the negative 2. Which would be negative 2/4 x to the negative 3. Like, yuck, that's disgusting. Okay, not only is it disgusting, so one of the secrets about L'Hopital's rule is that when you take derivatives, the powers get smaller. This power, in a way, got bigger in terms of I've got more x's now. I have x to the negative 3. So instead of my x's disappearing, they just got more disgusting. Okay, so it turns out there is a trick to this problem. And I'm going to show it to you, but first I got to erase my board. All right, we're back at it from the beginning with this problem. So what we're going to do, the trick that I wanted to show you is that a lot of times when you see trig, you want to flip it, which is a good instinct. But sometimes it becomes a bigger mess, which is what happened in the last problem. Instead, what I'm going to do is I'm actually going to flip this guy. So what I mean by that is that this would be the same thing as the sine of 1 over 4x squared over 1 over x squared. That is equivalent. Okay, this is beautiful. It's beautiful for many reasons. One is I feel much better about taking the derivative of sine rather than taking the derivative of cosecant. And secondly, I want you to notice these two guys. What's going to happen when I do L'Hopital's rule is that these derivatives are going to basically be proportional and make things really cute and clean it up. Okay, but let's make sure that I get infinity over infinity or 0 over 0. If I plug in infinity, I get 1 over infinity, which is 0. The sine of 0 is 0. 1 over infinity is 0, so it does check out. Okay, so we're going to use L'Hopital's rule. Here we go. All right, the derivative of sine, cosine. The derivative of 1 over 4x squared is 1/4 times negative 2x to the negative 3. Okay. The derivative of 1 over x squared is x to the negative 2, so that'll be negative 2x to the negative 3. Okay. And here's the beautiful part I was telling about. Even though this was disgusting, what happened is by chain rule of the top and the derivative of the bottom, those guys are going to cancel out. I feel like screaming and yelling. It's like, yes, woohoo. Okay, so now when I plug in infinity, I'm going to get 1 over infinity, which is 0. The cosine of 0 is 1. And I still have a 1/4. My answer is a 4th. Okay, so you're going to see in my solutions in my homework that some of these problems are a little crazy. It is just trickery and manipulation. But if you can find the trick, then you should be home free using L'Hopital's rule. So good luck. I know this video was a little bit longer, but hopefully it helps.